Hello everyone. Tech good reads give you good thing to read to listen. In today's video, I will talk about distributed ID generation. In today's content, I will first talk about what is distributed ID and the different ways to generate that ID. When we want to build a large distributed system, we need a unique ID to identify a group of data. For example, we need ID to identify each user, bank account number, order, message ID, etc. Thus, we need to build a distributed ID system. It should provide the following features. First, the ID must be unique for a single business. And another requirement is that maybe different system is different. Some of them have a fixed size, maybe characters, maybe long number. In some cases, this ID should be in sequential number. Some of the system require this ID to be sortable, like tweets ID, Instagram image ID, etc. If the ID is sortable, then the client can use the ID to query a range of ID. So this will be a very efficient way to get the latest updates. Let's see the different ways to generate that distributed ID. The first solution is UUID. It's global unique, but is not monotonic increasing. The UUID has 128 bits. Usually this can be expressed in 36 characters. In the RFC protocol, there are 5 methods to generate such UUIDs. Using the UUID, the good thing is that it's very high performance because it's generated in the local and there's networking costs. The cons include that this UUID needs 128 bits and this is too long for storage and in many cases to use such ID. And such a UUID has no order and it cannot be used as the DB primary keys and some other cases. Also, the UUID include a part of the MAC address, and this MAC address can be leaked. The second solution I want to talk about is the MySQL Cluster. It also provide a global unique ID and is also not monotonic increasing. If we only have one MySQL, we can use auto increment to generate ID for each MySQL instance. For this solution is monotonic increasing, but only one MySQL database is not very efficient, so it cannot handle a very large QPS. If we want to scale this MySQL, we will use MySQL Cluster. And for each MySQL, we set a different offset and increment. We can see as a right side of picture, we have 3 MySQL instances, and the first MySQL will generate ID 147, and the second MySQL generate ID 258. Using this MySQL cluster is solve the single point of failure issues, but also it has many cons. The ID is not monotonical increasing. For this solution, it's also difficult to scale horizontally because that when adding a new instance, you need using a new ID and maybe you need to adjust how to allocate these IDs. This solution also highly depends on DB availability. And since the MySQL is the storage, it interferes I/O, the DB is still the performance bottleneck. The next solution is introduced by Twitter is the Snowflake. It provides a global unique ID, but also this is also not sortable. It totally has 64 bits, and we can see at the right side of picture, it includes a 1-bit sign, 41-bit timestamp, 10-bit worker ID, and 12-bit sequence. Since that timestamp is at the higher end of these bits, it kind of provide a sortable for those IDs. But of course, if you have several servers, maybe some of the message are mixed up. Since this solution doesn't depend on the database or such a storage, this distributed system can survive dying nodes. The cons for the Snowflake is that this solution is highly depends on the service clock. And also this solution requires Zookeeper to keep a mapping of nodes and machine IDs. Introducing the Zookeeper have extra complexity. Snowflake is a very important solution in this area, and many companies adapt these design solutions to their business. Like Instagram ID generation, it changed some of the logic. We can see it use 13 bits for shared IDs and 10 bits for auto-incrementing sequence. Also for this shared ID, Instagram use logical shards mapped to the physical shards. For this ID generation solution, the auto-incrementing sequence can use DB auto-increment. Also for the mapping of logical to physical shards, it reduces efforts of resharding. When the system needs a scale horizontally, the developer can map the logical shards to the physical shards. Another benefit of this solution is there's no need to use Zookeeper, and this reduces the system complexity. However, this solution still highly depends on the server's clock. The next solution provided by the Meituan, and it has a leaf ID generation solution. It has two implementations. One is by segment, and the other is by Snowflake. Both solutions provide a global unique ID, and also the ID is not monotonic increasing. Let's see the leaf segment solution. Instead of using the DB to get auto increment ID each time, we can use the ID to generate ID segments. It provides a range of the ID generated, and for each leaf, it can just store this DB ID range in the memory and then allocate to the requested service. The pros for this solution is a very high performance and provide a horizontal scalability. And the ID is 64 bits number, which meets database primary key requirements. This means that this leaf segment solution is very good for the internal services. The cons is that this ID is predictable. So for some cases, it is not a good solution. For example, if you use this ID as an order ID and it's posed to the clients, then the clients can use this ID to guess how many orders your service created every day. And this will leak the business secrets. To solve this problem, Meituan provide a leaf Snowflake solution, and we can see that this leaf will not depend on the database to generate the ID segment, but using the Snowflake, it will depend on the Zookeeper. For this solution is the extension of the Snowflake. And for the Snowflake, the work ID is generated by Zookeeper sequential ID. Using this solution, the ID is unpredictable, and this ID can be used for the external use cases. Next solution I'm talking about is DD Tiny ID. It's provided per base type uniqueness and also not sortable. As a right side picture, under the HTTP, we can see its route traffic to the different Tiny ID servers, and each Tiny ID server stores the ID segments, and they will depend on the database clusters. This is just the extension of the leaf segment. And the difference is this architecture supports multiple DBs. Another important extension is that it does not only provide HTTP to the clients, but also provide a Tiny ID client. The Tiny ID client provides the following features. It stores the local generated ID, and in this way, it's a very, very high performance. And since these ID are stored at the client side, it will send a less request to the server. Thus, the server have a less traffic, and also the client side usually can serve the ID from their memory. This Tiny ID solution provides a higher availability. The last ID solution I want to talk about is WeChat Stick Serve. It's a provided per user uniqueness, and this solution is monotonic increasing. Let's see how we provide such a solution. For the port type, it has tables for each user, and each user has a current sequence ID. One problem we need to solve is how to ensure ID monotonically increasing. For example, if we have one server to provide a sequence, if the server needs to restart, then maybe the ID is not monotonically increasing. For the SQL, it uses the two parameters. One is the current sequence and the other is max sequence. All these two values are stored in the memory, and the max sequence is persisted. Each time for this server, if there's a request, the current sequence will add 1. If the current sequence reaches the max sequence, then it will increase the max sequence and update the storage. If the server is restarted, then the new server will read the max sequence and then start from it to generate the current sequence. Just for this solution, if there's a server restart, we can see the sequence jump. But it's ensured that ID monotonically increasing. Let's see the SQL architecture. Each alloc server will store the sequence in the memory and send back the ID to the clients. For the max sequence, it will be persisted in the store. An interesting problem to need to solve is that clients need to access which alloc servers. This will depend on the router. For each alloc servers, it only possess a specific range of the users for the ID. And this will be defined by the arbitration service. The arbitration service will depend on the current alloc servers to update the router in the store. When the alloc server requests to the store, it will retrieve back for the router. Then this will propagate it to the clients. If you need to further understand those solutions, please see these for the reading sections. Thank you for watching. This is Chinese. See you next time.